This is a demonstration of the LPP combustion fuel vaporization technology used to fuel a Capstone C30 30 kilowatt microturbine generator. LPP stands for lean, premixed, pre-vaporized. The technology allows for the vaporization of liquid fuels into an inert atmosphere to produce a gas with combustion properties similar to those of natural gas. That gas, LPP gas, can then be used to fuel virtually any combustion device. In this demonstration, LPP gas is produced from natural gas liquids and is used to fuel a microturbine to produce power. The microturbine uses lean premixed combustion technology, so the system is lean premixed and uses pre-vaporized fuel, LPP. This is a standard Capstone C30 30 kilowatt microturbine. The Capstone engine hasn't been modified at all. It's configured to run on natural gas. Capstone guarantees NOx emissions to be less than 9 ppm and CO emissions to be less than 40 ppm, corrected to 15% oxygen when fueled on natural gas. And the heat rate on a Capstone C30 is 13,100 BTUs per kilowatt hour. You can get these turbines in either a standalone configuration where they can start up on batteries and then provide power to an isolated load, or a grid connect configuration where startup power is provided by the grid, and then once the generator is producing power, the generator is simply synced to your grid. This turbine is set up in dual mode, which allows us to use it in either a standalone or a grid connect configuration. We've got it connected to the grid right now. So this is the LPP system. To provide the turbine with LPP gas, we vaporize liquid fuel in a vaporizer while mixing in diluent gas that both helps in the vaporization process and changes the combustion characteristics of the resulting gas fuel. We have a process flow diagram to help explain the process. This is the microturbine and the microturbine's exhaust. This is the heat transfer fluid reservoir. Heat transfer fluid is circulated between the exhaust heat exchanger and the vaporizer, and then back into the reservoir using this pump. Liquid fuel is injected through atomization nozzles into the vaporizer, where the fuel droplets are instantly vaporized on the hot walls of the tubes. Diluent nitrogen is injected into the vaporizer tubes as well. There are flow control valves and flow meters on both the liquid fuel line and on the diluent nitrogen line. LPP gas exits the vaporizer and enters the microturbine's fuel control system. Here are the components of the LPP system. This is the heat transfer fluid reservoir and pump, and then in the microturbine's exhaust, there's a heat exchanger. Heat transfer fluid is circulated between the exhaust heat exchanger and the vaporizer using the pump. All the heat necessary to vaporize the liquid fuel is provided by the exhaust heat from the turbine. This is the vaporizer. Fuel is sprayed through atomization nozzles into these two tubes, which are kept hot by the circulating heat transfer fluid. When the liquid fuel is sprayed onto the walls of the hot tubes, it vaporizes, and diluent is added into these tubes as well. The resulting LPP gas comes out of the vaporizer and runs straight into the turbine's fuel control system through this insulated line. The line is insulated to minimize heat losses from the LPP gas and the potential for fuel condensation. The temperature of the LPP gas needs to stay above the fuel's dew point to make sure no fuel droplets make their way into the turbine's fuel injectors, which would cause instabilities in the combustor. All of the control components are housed in these two cabinets. This cabinet contains all the flow control components. So we have shutoff valves, control valves, and flow meters for the liquid fuel and diluent gas. And then this cabinet houses all the electronic components. So we have data acquisition and control hardware, power supplies and relays, power distribution. This is where we are supplying the liquid fuel. This tank contains natural gas liquids under pressure, and here's where we're supplying the diluent nitrogen. For the demonstration unit, we just use bottles of nitrogen, but on an industrial system, we use air separation units. That's just an air compressor and a membrane that separates the oxygen from the nitrogen in the compressed air to leave you with an enriched nitrogen stream. This turbine operates at a pressure ratio of about 4:1. Its inlet fuel spec is about 50 psig. So we control our fuel and diluent to deliver LPP gas at that pressure. The diluent flow is actually tied directly to the liquid flow rate to maintain a certain ratio depending on the fuel. For an idea of fuel consumption rate, running at base load, nominally 30 kilowatts, the turbine will consume about 3 to 4 gallons an hour depending on the fuel and the heating value of the fuel. We have the ability to change the dilution ratio on the fly automatically with changes in liquid fuel supply. So we have an emissions probe in the exhaust, and we can monitor emissions here. So we're getting about 11 ppm CO. And 1 ppm NOx. And that's at 18.9% oxygen. So this computer is controlling all of the flows in the LPP system. We can control the liquid fuel flow and the diluent flow. And we control those flows with a pressure feedback to maintain the fuel inlet pressure. So on an industrial system, we would instead use a PLC and a touchscreen HMI for system control. Now this computer is used to control and monitor the Capstone microturbine. So it's running Capstone software that lets you control the system to command a start or stop or configure the settings. And you can also monitor performance of any of its systems. So right now we're looking at the power we're producing, about 20 kilowatts, turbine exit temperature, engine speed, fuel inlet pressure. You can choose from all sorts of parameters to monitor on both the combustion system and on the generator and power control systems. Thank you for watching and learning about the LPP combustion fuel vaporization technology. Please feel free to contact us with any questions.